I have done a bit of typing and I will try to explain via this PDF. I hope it will help you, although I request you to work out on your own because sometimes the symbols are not proper on the screen, so they may misguide you. Hence, I will explain what is that. So far we did some introduction to line integral. We obtained the problems. I had some problems on line integral, finding the values. Then we have stated the Green's theorem, and if I am not wrong, we have completed one or two examples on evaluation by Green's theorem. So evaluation by Green's theorem means applying the theorem to obtain the double integral. So that line integral is not obtained, double integral is obtained. So we obtained values using right hand side, that's why it is evaluate using Green's theorem. So this is the statement of Green's theorem where phi and psi are continuous functions and all that. So we have also obtained that work done problem. As you remember, we did all this work. We used the symmetrical form of straight line and all those things. We ultimately obtained the same answer 16. That's what. We got the same answer 16 for both of them. Now we have Green's theorem in the plane, and we have now applying Green's theorem to find the value where c is bounded by the lines x is plus minus 1. This also we have done in the previous class. We obtained the problems. Now let us come to, yes, verify Green's theorem. Yes. So first time we are going to take an example where we have to apply Green's theorem, not only to find the value, also we have to verify whether LHS and RHS are matching. So as it is written, the region enclosed is between the parabola and the straight line. We have very simple curve here. Only figure is missing in our presentation, otherwise other things are there. So you can see here y is equal to x is a straight line, and there is y is equal to x square. As you know, y is equal to x square always goes up, and it is in the first quadrant, so I will not bother to see other part, only I will look at first quadrant part. So y is equal to x square is here, y is equal to x is here. So there are two lines, we denote them by OA. One point is 0, 0. What can you say about the point A? Anybody? Yes, very easy to check. It is 1, 1. So the curves intersect each other at 0, 0 and 1, 1. Quickly, let us find dou psi by dou x. It is there. It is x, because what is psi? Just go up. Psi is equal to x square. So dou psi by dou x is equal to 2x. Psi is equal to x square. Yes. Dou psi by dou x is equal to 2x. So dou psi by dou x is equal to 2x. There is some mistake. And yes, what is dou phi by dou y? Okay, I have written the final answer, so don't mind. Yes, I have written the final value. I have not written them separately. So what is dou phi by dou y? X plus 2y. Yes. So when you take the difference, yes, it gives you x minus 2y. So I have directly written it. Dou psi by dou x minus dou phi by dou y is equal to x minus 2y. Now first find the RHS double integral, because it is very fast to evaluate this. Because you know the limits, just apply the double integral concept, take any strip whichever is convenient for you, and then get the desired value. So we are going to go for the vertical strip. So as it is mentioned, we take the vertical strip, y is equal to x square to x, and obviously x is going from 0 to 1. This point is 1, 0, and this point is, as we can see, it is 1, 1. So when you take that vertical strip, the order becomes dy dx, and hence we have to integrate x minus 2y dy dx. So if it is integrated, we get xy minus y square, because 2 gets cancelled for the second term. When you integrate between y x and x square and simplify. If you want, I will write it, otherwise you can check it on your own. I hope that much work you can do back. I hope back. That much work you can easily do. I repeat, that direct step I have written, yes, are marked 1, x raised to 4 minus x raised to 3. Before that, one step is there, I hope you will do it. So what is that? Substitute x as y and x as x square, simplify. So the first step, 0 to 1, xy minus y square, last step. 0 to 1, xy minus y square. This you simplify and make sure that you get the same answer as x raised to 4 minus x cube. I am purposely leaving it because then only it has some meaning, otherwise there is no point. If you don't work out, then there is nothing that will help you. So hence always prefer to leave something for you and just confirm it. Even the answer also I have written directly, minus 1 by 20. You can check integration. You can substitute 1 and 0. We get 1 by 5 minus 1 by 4. The LCM is 20 and then we get minus 1 by 20. So nothing is difficult. So this is the end of one part of the theorem, namely the double integral part of the theorem. Now let us go for the evaluation along the curves. So we have mentioned that we need to evaluate the line integral over C1 formed by y is equal to x square along the parabola going up. So this is your C1, anticlockwise sense. And we will come back along the straight line C2 given by y is equal to x. Got it? So first we have to evaluate along C1, namely y is equal to x square. Then we have to evaluate along C2, that is y is equal to x. So let us consider the parabola y is equal to x square. So I have mentioned that integral y is equal to x square, xy plus y square dx plus x square dy. Now, as I had mentioned, here also some steps may be absent, which we expect you to do. So can you tell me what part is to be done, which is not done? Yes, the function is xy plus y square wherever y is there. See, xy plus y square dx plus x square dy. Because y is x square, dy is 2x dx. Here you have to put everything. Then we will come to this expression x square plus x square dx plus x square dx. Is it clear? Yes? xy plus y square dx plus x square dy. So plus, so you can see first term x square, there is some mistake name. X square, so okay, sorry, first part, x square dy, so it is x cube plus x4 plus 2x cube, right, first part. So it will be 3x cube plus x raised to 4 dx, which is 3 by 4 plus 1 by 5, which is equal to 19 by 20. That was parabola. So I repeat again, we have to substitute. See here. So it is x cube, first term will be x cube, put it here. X raised to 4. This is no change. This will be as it is. But what is dy? 2x dx. Even this is not required, but better. If somebody is having any doubt, he will ask me. So hence, let us avoid that. So now you get it as 3x cube plus x raised to 4 dx, which you integrate and get the answer as 19 by 20. Now I'll go for the line integral y is equal to x, which is going to be taken as C2, and it will be going down. The same concept, same logic. Only thing is curve is going to change now. It is y is equal to x. So when you go for y is equal to x along the straight line, we are going to get it as x square plus x square and again x square. Dy is dx, so it is just 3x square dx. Answer is 3 times x cube by 3. Between 0 and 1, other way around, so it is minus 1. Now the line integral value over total closed curve C1 plus C2 is given by minus 1 plus 19 by 20, which is going to be minus 1 by 20. So earlier we have obtained the same answer by double integration, hence Green's theorem is verified. So as you can notice, if you know basics of geometry, then there is no problem regarding managing the value of the integral, because we are not doing much here. What is there, what equation is there, we are replacing. and corresponding differential also we are substituting. If y is x, dy is dx. If y is equal to x square, 2x dx. Whatever, y is equal to x cube, 3x square dx. So there is very simple way of dealing with the line integral. Okay, next example. This is another example where the function is given as x square plus y square I minus 2xyj around the rectangle bounded by x is equal to plus or minus a and y is equal to b and 0. So base and that b. Now it is mentioned already that it is a rectangular region. Function is also given, so you can see what is phi and what is psi. Psi is minus 2xy comparing with phi dx plus phi di and this one phi I and psi j. So x square plus y square is your phi and psi is minus 2xy. So when you take that combination phi dx plus psi dy, you get x square plus y square dx minus 2xy dy. Now the line integral f dot dr becomes, so it should go to the next one line, but it's okay, becomes simply integral over line x square plus y square dx minus 2xy dy. So we have already obtained that value of phi dx plus psi dy. It is mentioned now C is bounded by the rectangle of length 2a and height or length b. So rectangle has length 2a. So this is your a, 0, and the height of this one is only b. So you get a rectangle like this. So you can call them as C1, C2, C3, C4. So C1 is line AB I am taking. So the value of x is 0, but y varies from 0 to p. So where is that line now? I have not shown here in the figure. So I have to show now. Just see, for C1, line AB, the value of x is 0, but y varies from 0 to b. So where is that line? Same. Yes. Line AB, the value of x is 0, but y varies from 0 to b. Sorry, there is a mistake. Value of y is 0 and x varies from minus a to plus a. So please note this correction. Okay. So please note, along AB, the value of y is 0. This is done in a hurried manner, so it is possible that some error will be there. So that's why you just observe what I am telling. Y is 0, you do that first correction, and x varies from minus a to plus a. As you can see in the limit also, it was done in a hurried manner, that's why it is happening. Clear? X varies from minus a to plus a. It is not y varies from 0 to b. So obviously this is your C and this is your D. So we have called this as C1. Please do the correction. Along AB, that is C1, x varies from minus a to a, value of y is 0. So do the correction, y is 0 and x varies from minus a to plus a. So the integration is, yes, just see that expression. We have y is 0, so dy is 0. This is also 0, so it will be only left with x square dx. Now this is even function, so you can write 2 times 0 to a x square dx, which is 2 by 3, to a cube by 3 because limit is a. So 0 to a will come and it will be a cube by 3. Go, okay. Next, let us see C2 is at least correct. Yes, for CT, yes, C2, BC, x is equal to a, correct? This is the distance from the origin, x is equal to a along the x-axis, and y is now weighing from 0 to b. This is okay, this is correct. So for C2 along the line BC, x is a and y varies from 0 to b, so that integral C2 phi dx plus psi dy. So if you look at that expression phi dx plus psi dy, previous. So I will keep it ready here so that every time we can just think. This is your expression which is to be used every time. So now when we are in this curve C2, x is a, so we can put this as a, right? X is a, so C2, yes, x is a and y varies from 0 to b. So y varies, so x is a, so dx is 0, hence there is no first term. X is a, so this will remain, and y is varying, so it will remain as 2a by dy. And hence we have 0 to b, 2a by dy. I hope this is clear. we are putting the value, and then wherever differential is not there, we are going to ignore. Although a is there, but a square is there, but d will be gone because differential is not there. Clear? So we get that answer as minus ab square. Again, very simple integration. Minus 2a y square by 2. I have not written that step purposely. So 2 gets cancelled and we get minus ab square. Now go for the next curve C3, CD. See here y is b because this distance is d. This distance is b. So y is b, and now you see x is going from negative to positive. Correct? So we have to maintain direction, we cannot change. Hence, we have to take the limits of x as plus a to minus a. Hence, phi dx plus psi dy. Remember, dy is 0 because y is b. So dy is 0, this will not come now. This will come, y is b will come, we will get x square plus b square dx between a to minus a. You can see here, a to minus a, reverse limits. So you can write plus 2 times 0, minus 2 times 0 to a x square plus b square dx if you want so, minus a to plus a. Otherwise, take it as it is and you will get the final answer. If you want, I will write that integration x cube by 3, 1 minute, x cube by 3 plus b square x, correct? Between minus a, this way, plus a to minus a. So you can write minus a cube by 3, minus ab square, minus a cube by 3, minus ab square, because both become negative as the second limit. Hence we get minus 2ab square, correct, minus 2 by 3 a cube. Simple step, nothing is to be explained. I repeat, this becomes minus a cube by 3 minus ab square. Second limit, because of that it is minus a cube by 3, again minus ab square. So it is minus 2ab square minus 2a cube by 3. Yes, this is the end of second line. Now take the third curve, C3. Yes, C3 is over, sorry, C4. So if you take C4, the line is DA, correct? This is your line DA. So what can you say now? Anybody? X is equal to? Yes. What can you say about this line? It's a line parallel to y-axis. So what is the equation normally written as? X is constant. Are you sure? X is constant is correct? Yes, obviously, because that is the point where it cuts. So x is equal to minus a is the equation. So we have to substitute x is equal to minus a. Is it there? Yes, x is minus a. What is dx then? Obviously 0. Hence, this part will not come. I repeat again, x is minus a once again, and hence dx is 0. I have not written here. Every time not required, once you understand it's over. So then we see that y is going down this time from d to a. So the limits of y are going from b to 0. So just see, when you have some orientation or direction, keep on taking the corresponding limits, whatever they may be. Normally they must be in increasing order, but in this case when the line is considered, what order they are having, the same has to be followed. Clear? So again, we are going to substitute x is equal to minus a, and hence the second term becomes plus. It will be 2ay dy. Is it correct? 2ay dy. Where is it? Yes, 2ay dy. And what are the limits of y? B to 0. So when you integrate this, you get y square by 2, and we'll get the answer minus ab square, right? So minus ab square is the last curve answer. We have obtained all the line integrals, namely C1, C2, C3, C4. What we do now, add up. If you add and if you get that answer, what we got as the this one, what is that? Double integral. Then it is going to be tallied. Now on adding, we first of all get it as minus 4ab square. So minus 4ab square is the value on finding the line integral. Now we have to check that the same answer is going to come to find the double integral. Now I mentioned which is same as RHS double integral. Instead of that, it should be read as which has to be. So please correct such things. Means just remember, by mistake it has come, which has to be same as. Because we have not obtained the answer, we have not obtained that value. Unless you find, you cannot conclude. So I am saying it is same as, it is not so, it is has to be same as. So then we have to check whether it is coming, and hence we evaluate the double integral. So let us go for the double integral. Quickly you can see what is dou psi by dou x minus dou phi by dou y. Dou psi by dou x, partially differentiating this with respect to x, because this is your psi, this is your phi. So dou psi by dou x is minus 2y, and dou phi by dou x is 2x. So what we get in the end is minus, it is dou phi by dou y, sorry, so it is minus 2y, this, dou phi by dou y. So it is minus 2y minus 4y, minus 2y. So it is going to be minus 4y. You are subtracting this you are subtracting. So minus 4y, you have to integrate over the region R, and anybody can tell the limits of x in this case. Somebody? What are the limits of x, sir? How far it is moving? It is moving from A to B. Vertical strip, horizontal strip, they don't matter here. Limits are constant. What about y? Obviously 0 to B. Hence, this integral, we have written 0 to A, minus A to A, 0 to B, minus 4y dy, which is 1 minute we will get it as minus 4ab square, which is the LHS obtained earlier. Hence, Green's theorem is verified. So, if you take proper care in the direction, sign positive, negative, there is no way you can get it wrong. Only by chance, instead of writing plus, you write minus, then only such a thing is possible. So, I hope you have made that correction in the first curve. I hope you remember that first curve in that example. I told that this correction is there. I will make it afterwards, but right now you have to correct it. So, before uploading, I will do that correction. So, message will go. Got it. Yes. Anything next? Now we have an interesting result for the area of a plane region in terms of line integral, which is quite expected also, because after all, what Green theorem is saying? Green theorem says that I can link the double integral over that region given to me with respect to what line is forming that region. If circle is there, that circumference of the circle. If square is there, boundaries of the square. If triangle is there, boundaries of the triangle. So what is enclosed has a link with what is along the lines. 1, 2, 3, it depends. So that's why even this is also an expected result. So let us put phi is equal to minus y, psi is equal to x. So what will happen to dou psi by dou x? Psi is x, so it's 1, minus of minus 1 is plus 1, sorry, plus 2. Hence, the RHS of Green's theorem becomes 2 times dx dy. Because what is the Green's theorem? It says psi y, psi x minus phi y integral. Phi x minus psi y. That is, sorry, phi dx plus psi dy. That double integral goes on the right hand side. This. So, what is the original expression? It is double integral r psi x minus phi y. But what is that we have seen? It is 2. Hence, it is 2 times dx dy. Now, take 2 outside. What do we mean by just integrating between x limit and y limit? Very well known application of double integral, area of R. Thus, we obtain the answer 2 times area, and hence the statement can be written as, if you want to find the area, then it is, I will not write this symbol, directly write, what is that, x dy, y dx minus x dy. Now, this link is there, but definitely it may not be so fast method. Link is there, connection is there, but it is not advantageous, because integration is not ordinary. If you are using this Green's theorem, the integration will not be ordinary double integral. What you have to do is apply this formula. So, double integral you know, it is not new to you. So, now what is new? Line integral. Hence, apply this formula, get the answer. Hence, it will not be so fast, because depends upon the curve. Na? Once rectangle is given, how many curves are there? 4. On 4, you have to evaluate and get the answer for area. Got it? So, this is the problem. And that expression is fixed. Y dx minus x dy. So, you have to take like that only. Obviously, all this is in the plane, not in the space. Clear? So, using Green's theorem, this is an outcome relating to area. We see one example, although it's a bit lengthy, we want to show how it works. Although it is a bit lengthy, I accept. What is the question? It is a famous question. Famous because throughout second year also you have done that by various methods. Even in problems on area in double integration also you might have encountered that. So the question is, find the area between the parabolas y square is 4ax and x square is 4ay. The very first thing that I will do is draw this curve. So this is opening to the right side. So what is the equation of that? Y square is 4ax. And this is opening to the left side in the above. So it is. So please write important things. What is representing what? I could have used different color, but it's okay. You are good enough to manage this. Right. So I write y square is equal to 4x and x square is equal to 4ay. These are the two curves. Now you only tell me what is the way to proceed. Already one example you have done in the beginning, just today also. Just mark these points, coordinates. Quickly find the coordinates of this point, somebody, I am waiting. Call this first curve as C1, second curve as C2. Clear? You know the region, you know the boundaries. So mark them as C1 and C2. Anticlockwise you have to go. You observe x square is equal to 4ay, y square is equal to 4ax. Intersect at. Yes. Intersect at. Anybody? Yes. They intersect at 4a, 4a. Anybody can check it? You substitute y is equal to 4a, x is equal to 4a. You observe that both the expressions give you 16a square equal to 16a square. Clear? Routine work. Now just see how we have written. The area is to be obtained by line integral because we are using Green's theorem. Hence, I have written half c y dx minus x dy. So I have split into two parts. Half c1 y dx minus x dy plus half c2 y dx. You can take a half common also. It's okay. Next. Just see for C1, the parabola line OA of y is equal to x square by 4a. Parabola line y is equal to x square by 4a. dy is equal to x by 2a dx because you are replacing y by x square by 4a. So see the line. This is y square is equal to 4x. So see x square is equal to 4ay. This is actually the below parabola. This is below parabola. This is upper parabola. So y is equal to x square by 4a. So dy is equal to 2x dx by 4a. That is x by 2a dx. What is the value of x? X varies from this end to this end. So this coordinate is 4a 0. So x varies from 0 to 4a. So what you have to integrate now? We have to integrate x from 0 to 4a. That this one integration y replaced in terms of x. So just see here, you get this. You simplify, you get that 1 by 4a. 1 by 4a is taken common because if you take the difference, half minus 1 by 4 is always 1 by 4. Anything a is there, that's okay, but always half minus something is, sorry, half minus half of that is that one. So half minus 1 by 4 because 1 by 4 is half of half, right? Hence it is 1 by 4. It can be extended. So you can obtain the answer as 16a square by 3. Just first answer is 16 x square by a square by 3. Now again there is a correction. This is C2 which is there here also. There will do. So hang okay, afterwards. So for C2 parabola line OA, x is y square by 4a, as you can see here. This is the line. X is equal to y square by 4a. So dx will be written as y by 2a dy. What is happening to y now? Because you are replaced in terms of y. Y will be going from 4a to 0. So please make this C2. I am telling you, please make this C2. Because once it is uploaded, we cannot do anything. And just make sure that this is made as a C2. So please do it. Parabola line AO of x is equal to y square 4a. Dx is y by 2a dy. Y varies from 4a to 0. As you know, you can see it is going down from 4a to 0. It is like this. Hence, the integration is 1 by 4a. 4a to 0 minus y square dy. So y dx, what is happening to x? X is substituted. What is dx? Dx is also substituted. So 4a to 0, y is y only. So what we get? Yes, y dx minus x dy. Y dx minus x dy. Y dx minus x dy. So y is y only. What is dx? So it is y square by 2a. Then x dy. What is x? y square by 4a. So what you'll get, y square by 4a only, dy is as it is, so you'll get that same 1 by 4a minus y square dy. Is it correct? Minus y square dy, just check it. Of course, because the limits are 4a to 0, so your answer will be plus only, don't worry. Now finally adding the two values, first curve and second curve, we get the area as half times 16a square by 3 plus 16a square by 3, which is 16a square by 3. Average, correct? Is it correct? 16. No. Hence, we obtained the same answer 16a square by 3. Already you have done two ways. One way was finding the total area and subtracting, second year. Then this semester in application for area, we directly do the strip and then get the answer. We take the strip and get the answer. So that is second method. Now this is the third method. The answer is 16a square by 3. So we have used one problem to verify or illustrate how to apply the Green's theorem to find the area bounded by the curves, closed curves in particular. Now comes the next part, which is slightly tricky, but anyways you can manage it. You need not go in minute details, but I have just explained it in the form of some written things, written like this one. First of all, we are going to talk about surface integral, and the very first thing is surface word actually is a space word. So whenever you talk of 3 dimensions, surface comes. Oh, 11:15. So surface always comes in space, but that surface may be smooth also. It may be just plane also. It may be parallel to the plane also. For example, these walls of the room, the top, the bottom, the ground, and the left and right walls, they are smooth. They are surfaces, all right, but they are smooth surfaces. Correct? Then the question is how you identify a surface, how you define a surface, or what is the way to figure out this is a surface like that or this is a surface like that. And as you can see, if you remember the 3-dimensional geometry that if you have studied, if suppose you have studied, then there was a concept of plane in the space, and the plane was defined with respect to the normal to the plane. I hope you have some idea about it. When you want to define certain plane, what is most important is what are the direction ratios of the normal to the plane. Correct? So that you can identify that plane quite easily. Now you can see here it may be plane or any curved surface also. If a surface has a unique normal at each of its points whose direction depends continuously on the points of S, then it is called a smooth surface. If S can be divided into finitely many smooth surfaces, then it is called a piecewise smooth surface. Now you can see an inclined plane with all the coordinate axes, something like this, is one example. Sphere, showing it like this. Even ellipsoid, very similar to that. They are all the examples of smooth surfaces. Ellipsoid is also, because you can draw the normal easily. Anywhere you can go, you can draw the outward normal. Anywhere you can go and you can draw the outward normal. Only the point wise the value will change. So it's a continuous function everywhere. Hence, just as per the point that vector will come, there is no change in the procedure. The same procedure is there. Just find the gradient. So that's why knowledge of first sem vector calculus is required. Gradient of a surface represents the normal vector to it. Gradient to a surface is obtained by finding the is giving the value of normal to the surface. That is what we are going to use. Now a rectangular box, tetrahedron, pyramid are piecewise smooth surfaces. Simple reason, if you take a room like this, which is like a box, as long as you are on the surface, unit vector is there, normal is coming out. But as you cross this edge, the end, you cross the edge and come to this surface, the normal has changed. So piecewise it is in smooth. This part is smooth, that part is smooth, this wall is smooth, this ground is smooth. But there are in between edges where there is a total change. Hence, there is no unique normal vector everywhere. You have to find as per the surface, which is which direction and all that. And hence, a little bit of extra knowledge is required when you are talking about a surface. Okay, we'll come to that later. First of all, we'll see what is known as surface integral. Continuous, consider a continuous function fr defined over a patch of surface. I am showing this just for your sake. There is unique normal vector coming from this. So everywhere this function is defined. Don't think that this is your rectangle. You think that it is just a surface in space. I am showing for simplicity. It may not be rectangular, it may be any surface. Clear? So we have taken as a patch on it. Just see, we have divided into finite number of subsurfaces. So remember, surface is a two-dimensional thing, something. So when you are taking it, always it should be divided into rectangles, not straight lines. Divided. Correct? They are known as subsurfaces. Now let the surface element surrounding any point PR be ds. This is point P, ds. Now just see, we have written bold S to indicate that it's a vector. So just see this difference. Surface is not to be treated as some scalar quantity. In fact, it is not so. It represents something and it has a direction also. Just straight line is not a scalar quantity. Straight line is giving some direction. It tells which point it passes, etc. Surface is also like that. So very important thing that we should know. That is the only thing, that is something which we are not sure. Means we are doing it for the first time. When the surface is taken, the normal gives the direction and it is treated as the direction of that vector. So if surface is a vector, then what is the direction? Direction of that normal, outward normal. And what is the magnitude? What is that area? Because as I said, whatever be the patch, see, this is also surface. If you take this much, it is area. And what is outward normal? It will come like this. Towards you have to take. So that area is your magnitude and this is your vector. So there is a point-wise direction changing of the normal. And correspondingly area also will be having some value. Now just see the limit. Now you take this summation fr of ds. I am sorry, it should be f capital. So these minor things are going to happen. F capital must be there, f r ds. It's a vector function. So please do that correction. Small f is not there. It is capital F. So fr ds dot is there. Remember, dot is there. That's why it is not a scalar, it's a vector. Now, the limit of this sum as the number of subsurfaces tends to infinity and the area of each subsurface tends to 0. Routine definition that normally give for any definite integral, double integral also. If you remember double integral definition in the previous unit, you have done the same thing. That is known as normal integral or normal surface integral of fr over s. See this last line? It is called as normal surface integral of fr over s, denoted by, see the symbol, it is simply, this indicates the surface. If you write this bold, I have not written the arrow in the notes, it's okay. When capital is there, it is understood that it's vector function. So this can be written as n ds. Now you can see s is not bold. It is not bold. This is bold because it's a vector. So now it is not bold because it's a scalar. It's the area that is. So I have written the vector as unit vector into that magnitude. Normal method is like that only. I hope you remember. How you express a vector, a general vector. If you know the magnitude and direction, you can write it. So I have magnitude ds and direction n. So even n cap also we use, but it's okay. N ds is the corresponding vector. So other types of surface integrals are also possible. F cross ds. So this is double surface integral f cross ds. Obviously it may not have any meaning, but it is possible to get that answer. What is the answer? Will be a vector because it's a cross product. Similarly, if you just take scalar function, here the scalar is required. F ds means just multiply by some x, y, z, x square, y square, something, some expression. Then it is also going to be a vector. After evaluation, we will get it as a vector. Now, one important connection that we can give physically to this concept of surface integral is flux across the surface. And if I am not wrong, it talks about how many lines of force or whatever field is involved are passing through that. So if that is the case, if we mention f as the velocity of a fluid particle, then the total outward flux across a closed surface is the surface integral f dot ds. So direct connection between the surface integral and this flux can be given in like that, and hence we see that most of the applications of vector integration are connected with fluid motion. Most of the applications are going for field related things, and there is a separate, as you know, topic also known as field theory for ENC students, especially for ENC students. Okay. Now you can mention also, if it is taken as any other physical quantity such as gravitational force, electric force, magnetic force, then also you can find the flux by the same expression. So important is it is a field, vector field, and hence we can find the corresponding surface integral as the flux. Clear? So this is just the geometrical link between what is the surface integral with what physical quantities we can adjust or connect to them, right? Now comes the most important part, how to evaluate a surface integral for a given function, whatever f is there. So our interest will be in this part. We are not using this because we want this as scalar ds. So we can write it as something very easily. Vector is not to be changed, it cannot be changed, but scalar always can be managed. So let us see what is the way to manage surface integral or manage to find the value of the surface integral. Yes. We convert it into, that is a very important thing, it is to be converted into a double integral in any of the xy, yz or zx plane depending on the nature of surface. This is a highlight and crucial part of this one. You can just fix this in your mind. To evaluate the surface integral which is asked to us, we have to project it into xy, yz or zx plane and make it a double integral, which you already know. So very important, surface integral has no different procedure. See, surface integral, just like a line integral, does not have independent existence as such. It is made double integral. It is made double integral. Please fix these things because it's over then we will not have any problem. Also, you see here, we have to choose appropriate plane to project. For example, if I write x square plus y square is equal to 6 or say, then in space it is a cylinder with infinite height, radius of the circle is root 6, base is a circle of root 6. Agreed? Now you cannot project it in the xy plane because we don't get any surface if you project in the xy plane. Very important. This is your surface, correct? How can you project in the xy plane? It is a circle, it is not a surface. It is base of the cylinder. So if you want to project the cylinder, we have to either use yz plane or xz plane if it is x square plus y square is equal to 6. Similarly, one can say if it is x square plus z square, what plane you can select? If it is x square plus z square is equal to 9. So here what are the planes allowed? xz or yz. Don't take xy. Similarly, what planes are allowed? xy or xz. Sorry, yz. You cannot take xz plane. Very easy to remember also. Don't take that combination, take other combination. So many things in maths have link. Only thing is you should have patience and capacity to remember and reproduce. Because otherwise what happens, everything becomes trying to recollect and write. So some shortcuts are there. If I want to project this, then you should not worry. What is xz? Leave that. Take this or this project. So this way, projection is to be chosen properly depending upon the nature of the surface as it is mentioned. See here, plane surface is z is 0. You can take this as z0, your ground. y0, you can take either that or this, as per your choice, this or that, anyone, x0, depending upon which are the 3 coordinate axes. Now, any planes parallel to them will have normal vector as the axis to which it is perpendicular. Suppose it is xy plane, you know very well what is unit vector normal. It is k because it is z component which is going up. Hence, k cap is unit vector normal to it. Similarly, if it is yz plane, I cap will be or I will be the unit vector normal to it. So that is what we have mentioned. Then have unit vector as the axis to which they are perpendicular. Along the axis in which they are perpendicular. Next, just see the sign convention that we apply. This can be explained with the help of a box, a rectangular box. As you know, most of the packets, gift vouchers, etc. are packed in rectangular boxes. And even we have examples also on that. So if you take this box, you can see there are 6 faces pairwise opposite to each other. Now there will be some confusion regarding the unit outward normal. Hence we can see the outward normal coming out of the top is taken as positive, first line, and the other one going down is negative. This is very crucial because when you are evaluating a surface integral or using the Stokes theorem in surface integral, then with this care has to be taken which surface you are taking. Top one take plus, ground one take negative, going down. Similarly, right side, see here, the unit outward normal going out of right is taken as positive, going to the left is taken as negative. That's why box is the simplest example one can give, and we find in Grewal also many examples on box, because very nicely we can explain regarding this. Finally, this is also interesting, the unit vector outward normal coming towards us, if you look at this surface, which is coming out to me is positive, and the other one going to the other side, corresponding to the other side of this, is negative. So this is the sign convention adopted while dealing with the surface integrals, because if you don't fix it, you can't start. So our basic math starts with some fixed assumptions and everything we work on them, keeping that in mind without disturbing that. So here also we have the same thing. We have fixed these orientations of surfaces and the unit outward normals with signs as given. So please remember, this is a very crucial part of surface integral, because in examples you will not have any difficulty once you have this idea very clear. That's what. This can be explained easily in case of an entire box surface. Take all the 6 faces of a rectangular box, then it can be explained very easily on this. Now you can see the link, as I was mentioning, surface integral does not have independent existence. I was saying earlier, surface integral is not having independent existence. It is made double integral suitably, and here comes that formula, how to do which, what is the way. Yes, depending on the projection plane chosen, we have following formulae for finding the surface integral required. First, projection on the xy plane. Just see, I am saying xy plane, so definitely f dot n ds will become f dot n dx dy by n dot k. I was saying k is unit vector perpendicular to the xy plane, our base k. Obviously, for the other two surfaces, this and this, we have projection on the xz plane given by dx dz by n dot j, second one, see here, n dot j. The last one, obviously, what is the combination? N dot I, which will be yz plane. Thus, for all the 3 planes, we have a simple formula, and that is also not so complicated. See here, for all of them, there is a simple formula which is not so complicated. See, dy dz you are writing. What is the vector perpendicular to yz plane? It is I. That's why it is written as n dot I. So while computing, this care has to be taken. While computing the surface integral, this care has to be taken. Now, next, I have mentioned, please go through a solved example in Grewal. If possible, I will prepare and add if you want in the next class. Right now, I will only concentrate or focus on Stokes theorem, which is the major outcome of the surface integral that we have defined. Now, just see the statement of Stokes theorem. Let S be an open surface bounded by a closed curve C. F is equal to f1i plus f2j plus f3k be any continuously differentiable vector function. Then f dot dr is curl f dot n ds. So I am using normally arrow, but here it is not visible. Let it be. See the link, very important link. See the link. So if I ask an objective question in the exam, suppose, probably, then one possibility is Stokes theorem connects dash with dash. So what will be your answer? Faster. I am just writing it. You should tell immediately line integral and surface integral, or surface integral and line integral, whichever way you want to write it. So possible quiz question could be Stokes theorem connects dash and dash. Green's theorem connects dash and dash. One more Gauss divergence theorem comes, that I will tell later. Right now we will focus on Stokes theorem. So what it says, you just see, f dr is curl f n ds, but see the statement very carefully. The surface is open. Now you have a water barrel, you remove the lid, normal. The length is say 20 feet something, or I take 15 feet, but don't keep the lid, open it. Simple example. You take a box, rectangular, cut the face from the bottom or from the top, whichever you want. So when you get the gift, you open it from top, all the sides you open, it becomes your open surface. Any doubts in this? What will happen to a sphere? How will you cut? You decide one plane and cut the sphere. Just like how you cut some cake or something, bread or something. You have this continuous thing, just cut it from the center, you make it a semi-sphere or something like that. So any section you can take, yeah, watermelon is also there, you can cut from the center or any angle or any dimension, you will get that edge forming that open region. So watermelon, if it is like this, this is your corresponding circular open region, open surface. So all the others are closed. So that's why open surface, now they have mentioned bounded by closed curve. So this is the closed curve in one. So please remember what is open, from there the closed curve will come. So I have opened this, so this is your cylindrical this one. One single curved line. Clear? So curved line may be only single, it may be more than one. It depends upon the surface under consideration. What is that? Okay. See that link? It is curl f dot n ds. As we have mentioned, Stokes theorem connects line integral with surface integral in some particular manner. Again, if we take f is equal to phi I plus psi j, see Stokes theorem is in general for surfaces in space. Here we have changed it to plane, because I am saying if f is equal to phi I plus psi j, no z and k are involved, functions of x and y, then we get Green's theorem by just substituting. So I will leave it to you to do that. Clear? Any doubt? Yes, you will have doubt because I have not said anything. Yes, f is this. What is f dot dr? Phi dx plus psi dy. Phi dx plus psi dy. What is it? LHS of Green's theorem. Anybody having any doubt here? I hope no. F dot dr is f dot dxi plus dyj, so it is phi dx plus psi dy. Now that is ready, LHS. Now see what is RHS? Curl f dot n ds. Now we are in the xy plane. What is n? Anybody? We are in the xy plane. What is n? It has to be k cap. So k cap. What is the curl value of phi and psi? Just observe the curl value. I am writing the proof of that. Although it is not there, for your curiosity's sake, I am writing it. What is curl? Dou by dou by dou by. What are the components of the function? Components of the functions obviously are, you simplify within a minute, you will get dou psi by dou x minus dou phi by dou y into k. Got it? Now when you take the dot product there, because this is curl, you get n is k cap. Clear? Because I mentioned it. Hence we get this dou psi by dou x minus dou phi by dou y dx dy, because we have projected, we have taken the xy plane, so there is no question of any projection. Already it is xy plane. So dx dy will easily come, giving the Green's theorem in the plane. That's why Stokes theorem is better than Green's theorem, because it links in general. So luckily it comes double integral, that is different, simple one. But in general it is linking with surface integral, which I said is nothing but double integral with proper projection. Yes. So the Stokes theorem requires curl, and hence Stokes theorem as such is a time consuming job. Especially evaluation and verification of Stokes theorem. I will not say evaluation. If it is verification of Stokes theorem, definitely it is a time consuming job. Hence we are doing it because we must confirm the statement of the theorem. We just cannot leave it because it is lengthy and it is time consuming. So we must do at least few examples for verifying the Stokes theorem. So let us take the first example. Field is y minus z plus 2y. So what part is not there in the notes here, in my slides here, I am going to write in the board. Other part not required. So most of the times the vector part I have not written, such as curl and all that. So quickly let us find the curl value. We'll keep it ready. Later on we are using it. Y minus z plus 2. So I will give this 0, this will give you minus y. This minus this. Z is 1, hence y. Then j you can take plus j and take the order opposite. So this is minus 1, how much? How much it will be? Dou by dou z, what is the curl value? Just see what is the curl value. Plus j times dou by dou z of y minus z plus 2, which is minus 1, minus dou by dou x of minus 4x. So it is plus 4z. So it is plus 3z finally. It's not there. Down, down. Yes, it is minus yi plus z minus 1 into j. Now k does not come because there is no x here. There is no x. Dou by dou x, there is y. Yes? Minus 4xz, if this function is correct. If any correction is there, I will make it. Function. Verify Stokes theorem. Yz plus 4 minus 4zxk curl f. It is minus y minus j, that minus j or plus j, anything is fine. Z minus 1 into j plus z minus plus. Then lastly k dou by dou x 0. Okay, k times dou by dou x 0 and minus 1, so minus k, correct? Confusion? So it is minus yi plus z minus 1 into j minus k, we have mentioned it there. Now the surface is not shown in the figure in that our presentation, so I have to show that correctly as per the way we have taken it there. So please remember, curl is not available in notes. You write it separately, attach it there only, to that part only. So this part you can add it to your notes or that lecture. So let us write the solid clearly what they have mentioned, where S is the surface bounded by the planes x0, y0, z0. Imagine this, imagine this hall, the three faces. One is x0, y0 and z0. Then x is 2, y is 2, z is 2. They are cutting parallel to the xy plane, yz plane, zx plane respectively. So in the next class what we will do is we will extend this. We will find the surface integral values, we will find the line integral values. We will confirm that yes, Stokes theorem is verified. And after that we will try to continue with the next part of the vector integration, that is volume integration. And Stokes theorem and problems connected to surface integral require little bit more from your side as far as efforts are concerned. It takes little more effort from your side because projection and all those things are required. So I wish that you are studying properly and taking care and writing properly also in the exam that is coming up. Thank you very much. See you in the next class.